So off to the side, we're going to define what an odd function is. So odd functions are where the highest degree is an odd number. And the important thing from that we talked about before is that our end behavior acts like lines. If you have a positive leading coefficient, what does a positive line go? Up from left to right. If you have a negative leading coefficient, the slope would be negative. It would go down from left to right. So when we're talking about the end behavior, we're wondering where does it start and where does it end? And even functions of course, that is where the highest degree is even. The end behavior acts like parabolas. Oh, yeah, it's bugging me that I spelt it the American way. There we go. So what does a positive parabola do? So if you have a positive leading coefficient, your parabola opens up. If you have a negative leading coefficient, your parabola opens down. So now we can look at these. Now, in the chart below, it starts off with lines. Lines are odd, and so lines act like lines. Pretty obvious. If you have a positive leading coefficient, that's a slope that's going up from left to right. If you have a negative leading coefficient, that's a slope that's going down from left to right. When I'm talking about leading coefficients, what we're looking at is what's in front of the x, what's in front of the highest power. Again, same thing with parabolas. If you've got a parabola that the leading coefficient is positive, it acts like a parabola with a positive leading coefficient. And if you have a parabola with a negative leading coefficient, it acts like a parabola with a negative leading coefficient. And you've learned these already. But now we're going to go on to these next ones. What happens with an x cubed? The highest power is odd. It's going to act like a line. Can you see that it starts down here and ends up here? There's going to be possibly some crazy stuff that happens in between, and we don't know what that's going to look like, but at least we know it starts down here, ends up here. Here we have a cubic that has a negative leading coefficient. So we think about a line, and we know that it starts up here and will end down there. A quartic function, which is the highest power is the power of 4. A positive one is going to act like a parabola. So it starts up here and ends up here. And of course, there can be a lot of crazy stuff that happens in between. And a negative x to the 4 graph will act like a negative parabola. And so it opens down, starts at the bottom, ends at the bottom. And this pattern goes through. We could keep going. We'll stop at x to the 5. Here you have a positive x to the 5. So it acts like a line with a positive slope, meaning that it's going to start down here and end up here. Here we have an x to the 5 with a negative slope, means it starts up here, ends down here. And so we can use this idea of lines to help us figure out what it's going to look like at the end. Now in your textbook, they have this definition to help you remember it. However, and here's the odd one, I think it's much easier to think of if it's odd, it acts like a line. So if it has a positive slope, you just have to remember what does a line with a positive slope look like. If it has a negative slope, you just have to remember what a line with a negative slope looks like. For your even degree functions, instead of memorizing this, if it's a positive one, you know it's going to act like a parabola. So you can draw a positive parabola. If it's a negative one, it's going to act like a parabola this way. And I think these picture definitions are a lot easier to remember than as x goes to negative infinity, the graph falls to the left, and as x goes to infinity, the graph falls to the right. Whew. Makes sense, but maybe the picture is an easier way to remember it. Okay? So now we can take these and we can go and we can use that idea a little bit for our graphing. Some other key characteristics of graphing, we'll highlight these definitions here. Local maximum and local minimum points. So a local maximum is if you would just imagine these points as little cities. Somebody is the tallest in that city. Okay? And so you would say that that person is a local maximum because they're the tallest in their city. They might not be the tallest in the whole world. They might not, we would call that an absolute maximum, but they might be the tallest in their city. And so in a small area on your graph, if you have a maximum point at that, we call that a local maximum. This one up here is actually an absolute maximum for this graph. And, whoops. Here's another city. Somebody is the shortest in that city. And so they would be the local minimum. In this one, the graph goes down forever. So there's infinitely short people in this world if this was a graph talking about height. But that person is the shortest in their city. They're a local minimum, not an absolute minimum. If you really want to figure out how do you find those maximums and minimum points, make sure you take calculus next semester. So this is really leading into an area of calculus which helps you find local maximums and local minimums. For right now, you're going to have to rely on your graphing calculator to be able to find those. So we're going to do example 1. So we're going to graph these. If you have never graphed funny x cubed graphs before or funny x to the 4 graphs before, what strategy do you have that can always help you graph? Your graphing calculator, sure. But if you didn't have your graphing calculator, what are things that you can always do to graph? You can always make a table of values. Okay? So based on what we know so far, this is an x cubed graph. It's a positive x cubed graph. So we know that it's going to act like a line, meaning that it's going to start down there and end up top. As far as getting a more accurate look at what this graph looks like, you could plug in values for x. What are some easy values to calculate? 0 and 1. If you plug in 0, you're going to get 0. If you plug in 1, you're going to get -2. And then after doing 2 points, do you feel confident that you know what this graph looks like? 0, 0, 1, -2? No. Yes, you can close the door.
Try to do math, okay?
All right. No, that's fine. Let's pick another point. What would be easy to figure out? Maybe -1? Plug in -1, you're going to get -1 minus 3, -4. So we can get more values, and we could get more accurate. But based on these 3 points right now, maybe I'm going to do one more. I'm going to plug in 2. What happens when you plug in 2? You get 8 minus 12. Negative 4 again. Ooh, that feels
How would you just do negative 2? Just do
negative 4. That's down there. Ooh, I want to do one more. I want to do 3. What happens when you plug in 3? 27 minus 27, 0. Now I'd lose marks on this graph because I have nothing labeled, so if I label a couple of points, then it sets my scale up. So now I've got a bunch of points. I know that it has to start down here. So if we start going through the points, and I know that it has to end up here. So it gives me an idea of what the sketch is, but I'm not for sure that all my points are right. I don't know, for example, based on what I have right now, I could make it do all of these things and go higher there and lower there and steeper there. That would be still full marks based on what we have right now. We went through all the same points and the end behavior was the same.
Sorry for the interruption, just a really brief announcement. A reminder that the first musical rehearsal is today after school. All members with minds must attend for a read-through of the script. Thank you.
So for part B, it would be a negative parabola. You could do as many points as you needed to get a sense of what it looks like, and then you could graph it. I'm going to give you some questions to work on, 5, 6, and 8. We won't do the table of values, but this is a starting point. We know the end behavior, and we can use the table of values to get some points. And we're going to, throughout this unit, develop more skills. We're going to use our factoring skills. We're going to use intercepts to help us get a better idea of what is happening with the graph.